plenary talk given by Dr. Takumi Chikada. Please start.
Thank you, Chairman. So, good morning, ladies and gentlemen. My name is Takumi Chikada from Shizuoka University, Japan, and I have to talk today about tritium permeation mechanism in fusion reactor system. So it's more like experimental physics, not like theoretical one. And so this large device is ITER. It's called ITER. It's constructed in southern France now. And here we have a huge plasma vessel. And here we are constructing the tritium plant. So tritium is a hydrogen isotope, and it's a radioactive material. So then it's strictly controlled in the plant. So then I'd like to talk about tritium migration behavior in fusion materials. So let me start with where is Shizuoka. So Shizuoka is in the middle between Tokyo and Nagoya. It's the third or fourth city, largest city in Japan. So here is Shizuoka. And it's, so the Mount Fuji is the highest mountain in Japan. It's located in Shizuoka Prefecture. Then the green tea is the specialty of Shizuoka Prefecture. So, okay, then I'd like to start with a brief introduction, including fusion reactors are a new source of energy, found in ceramic coatings for fusion reactors, including materials. And secondly, I'd like to talk about hydrogen permeation behavior in ceramic coatings. So how to prepare and characterize the coating, and hydrogen as well as permeation, because the permeation is going through the material. So then I have to introduce some recent topics, including potential multi-layer coatings or irradiation effects from hydrogen permeation. And finally, I'd like to sum up my talk. So deuterium-tritium fusion reaction is the most promising fusion reaction because the high probability of fusion reaction at lower temperature, lower energy. Then we mix 14 megaelectron volt neutron and alpha particles, like helium nuclide, to produce energy. Then, so we need, anyway, we need deuterium and tritium. So these are the hydrogen isotopes. And in case of deuterium, we can collect from seawater because at 184 ppm contains the deuterium in the seawater. However, tritium has an extremely low concentration on the Earth, so we need to produce in the reactor. So the plan is that we produce tritium just outside of the plasma, so fusion reaction, using the high energy neutron. So if we set lithium around the plasma, so it makes some neutron reaction, nuclear reaction like this. Lithium 6 and neutron makes a tritium and helium. So we can produce tritium from lithium. Then we can collect lithium from seawater also. So the resource is abundant and sustainable energy system. So however, in the gigawatt class fusion reactor is a common power plant. So the plant system must produce and recover 100 kilotrillion per year. So it's a huge amount of radioactivity. So we need to control strictly to keep the safety outside the environment. So the strict control of tritium fuel system is essential for safe operation of fusion reactors. So this is the roadmap of the development of fusion reactors. Now we have experiments using some small size devices such as CD60s and JET, Joint European Torus in UK, Then it's going to head into ether. Now it's constructing. Then after that, this is the device for the plasma physics experiments, not like a power plant. So we need to confirm the efficiency and some energy efficiency and energy conversion in demo reactor, demonstration reactor. So in this case, we need to care about the tritium production and recovery system. So this is not like plasma physics, not only physical plasma physics, but also the engineering side. So then the problem is that the most metals for structural materials such as iron or vanadium or some other metals has a high permeability of hydrogen isotopes. So tritium permeation through the structural material fusion systems causes a crucial fuel loss. So it's around this fuel system is around here, then going through, so the leakage of the tritium makes a big problem. So very logical problems of that. Then another thing is that the liquid bridges, we are considering to use lithium containing material to produce tritium by nuclear reactions. So it makes some corrosion or structural corrosion or erosion in the pipe walls. So the basic plan, our project is to coat tritium impermeable thin film to prevent tritium permeation through the cooling channel or outside of the reactor. So this is called tritium permeation barrier, TPB. Then it requires high permeation reduction factor, of course. So the factor of 1,000 or more. Then compatibility with blanket materials such as liquid metal is a highly corrosive material. Then radiation resistance. So the fusion reactor makes a huge amount of gamma ray or neutron irradiation environment. So we need to confirm the compatibility with irradiation environment. So the history of the coating development is it was using basically aluminum oxide or silicon carbide or something like that. And the problem was that the much higher permeability than bulks when it coated with a thin film. So it's a much higher permeability. So something wrong with the thin film. Then the data is scattered. So for orders of magnitude. So it's a 10 or 100,000 or something like that. So that's a serious problem. Then we started using barium oxide. So it's a rare earth metal oxide and yttrium oxide to make a really clean and pure and flat, so uniform coating. And so it was originally selected as an electrical insulating coating, and it has a high thermodynamic compatibility stability. So this figure shows that it gives free energy of metal oxide. So it means really stable at a high temperature or some corrosive environment. Then compatibility with liquid lithium. This is alkali metal. And the good thing is lower crystallization temperature than aluminum is also good. So in this presentation, the decade-long research, so from my master course students of fusion permeation mechanism in fusion materials for the establishment of fusion reactor fuel cycle is really. So let's move on to the permeation hydrogen behavior in ceramic coatings. So in our studies, so we coat the barium oxide or yttrium oxide coating by these two methods, gas phase method and the liquid phase method. So gas phase method is a really experimental thing. So we use the vacuum chamber, and Van sparkling and vacuum up deposition is a rather common device. Then we can get good adhesion to the substrate and low impurity. then we can change the parameter of the coating very easily, just changing the deposition time or substrate temperature or something like that. So it's good for clarification of permeation mechanism. Then another side is more engineering. So the liquid phase method is just liquid organic material. So then the substrate is dipped into the liquid, then withdrew at the constant speed to coat the same uniform film. Then bake after that, so afterwards to decompose the organic material to then the metal oxide remains on the substrate. So this is good for plant scale fabrication, but it is a little bit difficult to coat coating property. So the thickness or crystal structures is not so easy. So it's more development of practical applications. So in the permeation physics on hydrogen isotopes, so permeation can be expressed by multiplication of solution in diffusion. So the hydrogen is solved in the material, then diffused into the material, then we combine at the other side and dissolve from the substrate. So diffusion is a fixed flow, and the solution is a zero flow, makes this equation. So J is a permeation flux at the per unit area and per unit time. Then this is permeability. This is the multiplication of Zivets constant and diffusivity in the material. Then this is the thickness of the coat. This is the thickness of the sample. And this is the deuterium pressure, hydrogen pressure at the high pressure side. So we constructed the deuterium gas permeation apparatus shown here. So here, just the two vacuum chamber, and the sample is located here. Then one side is filled with deuterium. Then permeated deuterium can be detected by quadruple mass spectrometer. Then we can compare the permeation flux with coating and without coating. So then we can calculate the permeation reduction factor. So the higher PRF means better barrier coating. So we are aiming to get some more than 1,000 or something like that. So this is some brief summary of our 10 years study of TPB coating. So this is the actually best coating in the world. So here, this is the iridium oxide coating deposited by vacuum arc deposition. 2.6 micron means this was coated on the both sides of the substrate. So when we coat on the both sides of the substrate, so the permeation can be reduced with two steps. So that means 100 and 100, something like that. So we found that just one side, the thicker coating, doesn't mean very good property. So we need to make some multiple boundaries to reduce the permeation. So the 10 to the power of 5 is the world record. Then we get the world record is not broken now. So this is interesting thing is that the permeation mechanism through iridium oxide coating. So this figure shows the permeation flux, temporal change of permeation flux is the first test, second test, and third test at the same temperature, so 500 degrees. So at the first test, when introduced the deuterium, so permeation flux decreased drastically during the measurement. Then when we repeat the measurement, so it's going down with the same deuterium pressure, then finally we get the steady state permeation flux is like this. So that means something changed in the films. So with the TEM observation, so this is a cross-sectional bright field TEM image. So the columnar structure is bigger after permeation measurements, then the permeation decrease. So that's some important change. Another thing is that this is a surface deuterium distribution with sinks. So then the grain structure is like this. So it's really close to the close network structure like this. So that means that grain boundary can hydrogen or deuterium can permeate fast at the grain boundary. So this is called the grain boundary diffusion. So the deuterium can permeate not in the crystal, but in the grain boundary fast. So this is the grain boundary is the main path for deuterium migration. So this is another topic, is that we always use deuterium or hydrogen to test permeation measurements. However, we have to use tritium to confirm the more realistic situation. So the tritium is radioactive isotopes. So we need some special equipment. So we, in the collaboration framework of Japan and US joint project, Titan, so we used the tritium with tubular sample. So this is a tube, and here is a aluminum oxide coated sample was buried with the other components. Then tritium is going through inside a tubular sample, and the permeated tritium was collected by purge gas, purge helium, to go to ionizing chamber to collect the tritium. Then we obtained that the coating on tube sample is also good, as good as plate substrate, plate sample like this. So the comparable here has been achieved also on tubular sample. So that's a very good news. Then not only the experimental, but also the computational simulation has been done with molecular dynamics and then density function theory. Then we constructed this system with so hydrogen is dissociated on the surface and absorb and penetrate in trapping or grain boundary diffusion. So this is a 5 steps migration in the coating. And we also constructed this idea on grain boundary structure, grain structure. So this is also experimentally confirmed by TEM observation. So this is a grain boundary. So then in the so as a result, so the formation, the diffusivity in the hydrogen, diffusivity of the hydrogen is 2 or 4 orders of magnitude faster than in the bulk. So the grain boundary diffusion is much faster than in the diffusivity in the bulk. So this is really this agrees with the experiment. So this is another analysis of with a computer simulation. So this is just a simple modeling with a coated region and uncoated region when we think about the peel off or crack in the coating. Then in the coating, we assume that the grain boundary diffusion. So then this is the permeation flux with the grain size of the coating with different surface coverage. So if we think about 90% of the surface coverage, so if we increase the grain size, so it isn't any change. So we need to cover 100%, so the grain size as the permeation flux decrease as the grain size increase. So the first priority is surface coverage in this case. So the materials and fabrication and with grain boundary structure should be selected afterwards. So we need to anyway coat the substrate perfectly. So then another thing is that the recent topics, so we are struggling to solve the problem. So this is some topic about the potential of multi-layer coatings, not only a single layer, but also that some other materials can be piled up to modify the coating property. So in case of the single layer coating, then when we pile up the iron metal coating, so this is good for the compatibility with liquid material. So this is the same permeation reaction factors. So iron didn't do anything for permeation reduction. Then when we think about when we coat iridium oxide again, so this is a three-layer coatings, so the permeation reaction factor is increased to 10 to the power 4. Then in comparison with the both side coated sample, so it's a little bit lower permeation reaction. So it means some dissolution or recombination process is important to at the back surface. So the permeation behavior is affected by recombination process on back surface. So it's one thing we found recently. So this is a more, not like physics, but chemistry. So some compatibility, so chemical stability test has been done. But so something, so lithium lead is a liquid breeder candidate, then it corrode iridium oxide gradually to then deteriorate the coating property. But with the multi-layer structure makes reduce the corrosion rate. So that's the engineering side is very good. So the outer layer reduce the corrosion rate. So then when we think about the different materials can be coated, so in this case, iridium oxide and zirconium oxide two-layer coatings makes much better coating property than single-layer coating. So in the single-layer coating, sometimes it's degrade after permeation measurement at high temperature, like 700 degrees C. However, this multi-layer coatings makes much better property at the high temperature after high temperature measurement. So that was the reason that so multi-layer makes some influence for the crack formation. So when the crack is introduced in the one layer, so the other layer doesn't have the crack formation. So that means the hydrogen cannot go fast. Just one layer is fast, and the other layer is actually normal. So uncoated area, the first process was covered by the coating at the second process. So the multi-layer is really good for the physics, the permeation physics side. So this kind of multi-layer coatings give us some implication that we can select structure. So application should be not only the fusion reactor, but also some hydrogen-related plant or some hydrogen storage tank or hydrogen production plant make some specific structural material. Then fluids such as hydrogen or some liquid, then temperature range is different, so room temperature to high temperature. So you can select the materials and number of layers and methods to optimize the barrier coating to satisfy the properties requirements. So another recent topic is that irradiation effects. So neutron makes defect in the coating crystal structure, then gamma ray makes some excitation to accelerate the tritium migration, maybe. So, but we don't know actually. So we tested with the gamma ray irradiation facility in Shizuoka University. So we have a cobalt-60 gamma ray irradiation facility. Then we have no neutron source so far, so because of some after Fukushima accident, so all nuclear experimental reactors is stopped to confirm the safety. So now we simulate the neutron radiation using the ion, such as the heavy ion radiation. So this is the Kyoto University facility. So I'd like to talk about the two topics about the gamma ray and the ion irradiation. So in case of gamma ray irradiation, we construct the permeation device very near to the gamma ray source. So this is quite special because we need a long tube to protect these some electronic devices, because the gamma ray destroys electronic devices very easy. So we need to make some distance to make a shield to the gamma ray source. So then here is gamma ray source, then the permeation part is here. So deuterium can permeate through this direction. So it's like this. Then here's the sample. So then this is called we call it Hyperion, hydrogen permeation system under gamma ray radiation. So with this system, so we tested just a steel substrate. Then steel, in case of steel, during the irradiation, the permeation increased. I don't know why, but we are struggling to solve this problem. But just 0.5% or something like that, up to 1% or something. Then the increase of permeation factor was proportional to the dose rate. So dose rate is important. So so increase of deuterium permeation through steel during gamma ray irradiation was firstly detected and showed the dose rate dependence. However, in case of barium oxide coated sample, there is no decrease of the permeation, no change. So it's like this. So in this case, so barium oxide coating mitigated the irradiation effect under the present irradiation condition. But in case of the fusion reactor, so it's a really high dose rate gamma ray. So in this case, we don't know. So nobody knows the situation. So this is the dose rate dependence and the temperature dependence. So at the high temperature, the increased rate is decreased. So we care about the lower temperature. It's a high increased rate of the formation flux was detected. So then in case of the ion irradiation, we evaluated barium oxide coating with ion. So Fe 3 plus 6.4 mega MeV ion was evaluated with up to 1 displacement per atom. So, however, the result was good. So after irradiation, the permeability decreased, not destroyed. so some crystallization or something like that is improved by irradiation. So of course, we have to increase the dPa, so displacement per atom. So this is the damage concentration up to 100 dPa, but so far up to 1 dPa. So the situation is very good. So in case of the yttrium oxide coating, so the irradiation makes amorphous structure and the voids, many voids in the coating. And after permeation measurement, so it increased up to 700 degrees C. So the amorphous was crystallized and voids was disappeared by recovery of the damage. So then the permeability is around 100. PRF is about 100 to 400 before and after permeation measurements. So we are struggling, we are now dedicating our effort to clarify that amorphous structure makes something in the permeation measurement, permeation property. So this is a summary of my talk. So the decade-long research of tritium permeation barrier coatings has been introduced. Methodology for the fabrication of high-quality aluminum oxide and yttrium oxide coatings were established using gas and liquid phase method. So permeation reduction factors of 1,000 to 100,000 were achieved also by the coatings on tubular substrates. Various permeation behaviors such as effect of grain growth, surface effects, multilayer structure, modeling, irradiation effects, and so on were found by microstructural analysis and tritium permeation agents. And ceramic coatings for fusion applications will broaden design windows for sustainable energy systems. And finally, we are always welcome you as collaborators. Feel free to contact me. So this is my email address. Thank you very much.
Thank you, Dr. Chikada. Any questions?
When will ITER start? When will RTER start?
Yes, that's a very good question. So now the construction time is long, so prolonged. Then now the recent, so the latest announcement was that the first plasma will really ignited at 2025.
So will live that long.
So 8 years later. Then actual DT fusion reaction will start with 2035. So it's 10 years later.
Thank you. Next question. There are not questions. Let's thank Dr. Chikada once again.
Thank you, Professor Chikada, for your wonderful presentation. Now I call upon Professor Anthony Shihab to come forward, please, Professor. And